How do cryostats create ultra-cold vacuum for quantum computers? Imagine trying to keep a tiny, delicate device at temperatures colder than outer space while keeping everything around it perfectly clean and free of heat. That's what cryostats do for quantum computers. They are special machines designed to make and hold environments so cold and so free of air and other gases that quantum bits, or qubits, can do their magic. These conditions are vital because qubits need to stay in a very fragile state, free from interference caused by heat or noise. The first step in creating this environment involves a sealed chamber made of strong, airtight materials like stainless steel. This chamber is pumped out with powerful vacuum pumps that remove all air and gases, creating an ultra-high vacuum. This vacuum prevents heat transfer through air and stops tiny particles from bumping into the qubits, which could disturb their quantum states. Think of it like trying to keep a delicate snowflake from melting in a windless, airless freezer. Next, the cryostat uses multiple cooling stages. The initial stage employs cryocoolers or pulse tube refrigerators that lower the temperature to just a few kelvins, which is close to minus 270 degrees Celsius. These coolers work by compressing and expanding gases to absorb heat. The final stage involves a dilution refrigerator, which uses a mixture of helium-3 and helium for isotopes. This mixture circulates through different chambers, removing heat through a process called dilution cooling, bringing temperatures down to around 10 to 20 millikelvins. That's just a tiny fraction above absolute zero, the coldest possible temperature. Achieving such low temperatures is essential because superconducting qubits need to be at these temperatures to exhibit zero electrical resistance and maintain their quantum states. The dilution refrigerator's operation relies on quantum properties of helium isotopes, which allows it to remove heat continuously and keep the environment stable. Vibration and thermal fluctuations can disturb qubits, so cryostats are built with special isolation systems. These dampen vibrations from the cooling equipment and block external heat sources. The vacuum chamber itself acts as a thermal insulator, preventing heat from entering from outside. Inside the cryostat, the quantum hardware is mounted on specially designed stages that provide both electrical connections and thermal stability. These stages are carefully cooled and shielded to keep the qubits at their required temperatures. Modern cryostats also include automated controls that monitor temperature, vacuum levels, and system performance. These systems can adjust cooling cycles or warm up the environment gradually, making sure everything stays stable without manual intervention. All these steps work together to create a perfect ultra-cold, ultra-clean environment. This allows quantum computers to operate with high fidelity, keeping qubits coherent longer and reducing errors. Superconducting qubits, for example, need temperatures below 20 millikelvins to stay superconducting and avoid losing their quantum information. Trapped ion qubits also benefit from cryogenic vacuum conditions, which reduce collisions with residual gases and help keep the ions cool and stable. In essence, cryostats are the backbone of quantum computer architecture. They turn the impossible into reality by creating the ultra-cold, ultra-clean environment needed for quantum phenomena to happen reliably. Advances in cryogenic technology continue to push the limits, making quantum computers more powerful and scalable every day.